Good morning, everyone. This is Mo and Sani. Welcome to our Marine Infrastructure Live podcast series. Today is our season 3, episode 5, and we're going to be talking about some of the tests that we have been doing to develop this new product, SPiRe Plus. Just FYI, I was out of the country for a couple of weeks. The first part of my trip was in Cartagena, Colombia, where we are doing a major jetty repair for Chevron. So I visited that job site, about 112 or so piles on that jetty. And then after that, I went to Peru, where we have finished the first phase of it, which was about 140 or 150 piles on a pier for an APM terminal, and that's done. And now we are getting into the second phase of it. So, and along the way, my iPhone and all of my credit cards were stolen. And so I can do a whole new podcast maybe on how to retrieve your stolen podcast. And there are ways to actually find the thief and all of that. But anyways, that's a subject of a whole different podcast if we wanted. So let's get into today's presentation. And here we go. All right. So what I want to talk today is about show you how we built these specimens that we were testing, some of the test results, and then some applications for these. I don't know, maybe some of you, when you were as a part of your studies as a graduate student, perhaps you did some testing or in a structural lab, but the majority of the engineers, they don't get a chance to play with concrete in the lab. So I thought this might be interesting for you to see, and of course the test results are always interesting to see how you verify those. So just to refresh your memory, these are about our SPiRe Plus panels that we are testing. These panels, as you see here, they are 3 feet wide, roughly, or 900 millimeter wide. And they have these T profiles every 4-inch or 100 millimeter on center. You see a typical panel in the middle, 3 feet wide. This one is about 12 feet tall. We also stock them in two lengths, 12 feet and 18 feet. And of course, they can be custom made or ordered to any length. And then on the far right, you see the back face of one, and the grit code or the T profile face is on the left, and then the smooth side is on the outside. The one thing to note in this slide, though, is that the panels, because these T profiles occur every 4-inch on center, we tested these. We took an 8-inch wide band of these for our testing. So in an 8-inch wide typical strip of this panel, you would get 2 T profiles, and that was the main primarily reinforcement for this section. So here is the construction of these. We basically, in this case right now, this is an 8-inch wide panel that is at the bottom of the form. So that becomes the bottom of the formwork, as well as all of your reinforcement and so on. And then around it with some 2x4s, we made a 4-inch tall formwork around it, as you see here, and then mix the grout. And the grout that we usually, when we use these grouts, we want them to be flowable, because in the field you will be pumping these from maybe on the land side or on a barge, you'll be pumping them. So we want to make sure that the grout is flowable. And as you see on the far right, this grout is fairly flowable. So we pour it in, it fills the formwork. So this was the casting of one of our specimens, which was 4-inch thick. We've done 3-inch and 2-inch thick grouts as well. So the next thing that they do, once because you want to make sure that you don't lose too much water from your grout mix because of evaporation. So we typically cover, moist cure the specimen. And one of the ways, a cheap way to moist cure a specimen is basically, while it is in the formwork or it is out of the formwork, you cover it with burlap and keep watering it. You could protect it with a plastic sheet so that it kind of keeps the moisture in there for the few days while it is being cured. And then on the right of this slide, you see our loading arrangement. So typically all of these, they were tested what we call here L1. That's the span. This was 9 feet for all of the specimens. And then we have a load spreader, which is basically a beam with two rollers like that. And the load from the jack is being applied to the middle here. So then half of the load goes to each of these through those spreaders, and then that gets transferred to the end support. So if this is kind of this schematic drawing of that, but if you look at the actual test setup is shown. This is our Quakerap R&D laboratory that, we do these tests. So on the left, you see the test frame and, like the typical details. So here you see on the forefront of the image, there is a roller, and then I pointed it, a close up of it on the right. So this, we use a roundabout, I think, it's a 6-inch or so diameter tube that becomes our support, so it acts like the roller, right? And then in the middle, from that red loading frame, you see that the jack and the loading is applied that way. So if I look at a close-up of it on the far right, you see that the jack is there, that we have a load cell. The load cell, we can read the value of the load being applied electronically. It comes to this dial gauge, which is to this basically this readout, which is the white one. And then above that, there is another reading, which is the displacement of the beam. So as we have right here at the middle between those two concentrated loads, you see that we are measuring the displacement of the beam. So we are going to be plotting applied load here versus the midspan deflection. And then on this one in the middle and the top, it shows that how the spreader or the distance between the loads was achieved. We have a couple of rollers that were welded to that plate, so that kept the distance. So the specimens, again, the summary of the specimens are shown in here. So we have beams, I'm referring to them B2, B3, B4. These designations, basically the B is for beam, and then the next digit 2, 3, or 4, those refer to the thickness of the specimen or the thickness of the grout that we used. So we had a 4-inch grout, a 3-inch grout, and a 2-inch grout thickness. The distance L1 for the testing the span was pretty much the same for all of them, 9 feet or 108 inches. This distance between the two loads, we used a 12-inch for the first one, which was this 4-inch wide or 4-inch thick specimen. And then for the other two, we did a smaller, that L2 was only 4 inches. I also have given you the dates of these. We tested the 4-inch thick specimen almost a year and a half ago in November of 2023. And then the 2-inch and 3-inch samples, they were tested more recently, last month, actually. And the applications of these, are the 3-inch one is typically for like seawalls. Usually we use 3-inch, or it could be 4-inch, but typically 3-inch. 4-inch can be used in, any really application that you may run into it if needed. And the 2-inch, which is fairly small, is for one application for construction of roofs that I'll be talking about a little bit more. So here is the test setup for the first one of these that we tested, beam B4. Again, remember, this is 8-inch wide, 4-inch thick, and we are applying the load in the middle. On the right here, you see this is the load deflection curve for this specimen. And as you notice, it goes to a load of 900 or 9,190 pounds, or roughly 9,200 pounds. And if you convert that load and a deflection of about 3 inches at the end, 3,000 thousandths. So it's 3 inches basically. And we can then convert that the load converted, knowing this distance of the moment on, we can calculate the moment capacity or the moment at failure for this 4-inch sample was 220 kip inches. So if you convert the moment failure moment of that is 220 kip inches, and by the way, if you look at this cross section down here, we only have the 8-inch wide panel of SPiRe Plus and two of these T profiles. That's the only reinforcement in this panel. There is no steel. So this moment capacity is basically from that 8-inch wide piece of the panel. And that, if you calculate it, you can see that if you had a concrete beam with these dimensions and you had number 6 grade 60 at 3.5-inch spacing, it would give you the same moment capacity. So it's kind of, it shows you how you can equate these two systems together. Then during the testing of these beams, we measure, look at the cracks in the specimen, and you'll see in another video in a minute, I'll show you, but we mark the cracks along the flexural face of the beam. And in all of these specimens that we've tested, we noticed that there is a good distribution of cracks along the beam. You don't have all of the cracks concentrated in the middle and not much on the, on the lower, this left and the right hand, where the moment is less than the midspan of the beam. This indicates that you have very good bond between this SPiRe Plus panel and the concrete or grout. And that's really achieved because of that grouted surface that we have, plus the fact that that T kind of like holds them, locks them together. So that is one of the things that we were observing from marking of those cracks. And the failure of this first specimen, we noticed that it happened, it was very abrupt and suddenly it failed. But one of the T, remember it had two of these T profiles in that beam. One of the T profiles failed. The failure was because of that failure between the flange and the web of one of the T's, okay? And as you notice, this test was done almost a year and a half or 2 years ago in November of 2023. So once we saw this failure, then we changed the design, and in our next series of SPiRe Plus panels, we have beefed up that connection of the web of the T to the flange and added some more material in there to make sure that is strong and it doesn't fail there. So the next two beams that I'll be talking, B2 and B3, they were built with this newer version of our SPiRe Plus, which is currently it's the only one that we are making. So that's what everybody's getting now. So this is one of the one that is 3 inches. By the way, we went with the 3-inch thickness because in most of the seawall repair projects that we do, you have about a 3-inch annular space. So that was a good reasonable number. And then here you see that the load of this thing, again, we're testing it over a 9-foot span, but the distance between the loads is 4 inches. And we have the data here. They'll be also listed in another table that you'll see later. But this is for this 8-inch wide, we achieved the moment capacity of 204 kip inches, for example. And so this is actually a video that I'm going to share with you. This is the video of the test that we did and how it goes to the failure. The actual test took several minutes, but I have speeded up the video for you so you can watch it. Let's watch this video to correct. Yeah. As you see, it starts loading, deflecting. Then we have George coming by and marking the flexural cracks in this. We did that a few times during the testing. And once the cracks were, then it goes all the way to the failure. And watch it. Yeah, here it goes. So the failure again was, maybe if you want to watch this again. So the failure was sudden, and it was by compression failure of the grout. We didn't have that failure of the flange to web like we had in the 4-inch one that we had tested before. So the test was, pretty good and successful. There we go. It goes there. Okay. So the next specimen that I wanted to show you was the one that we used only 2 inch of concrete or grout. So this one, when we first tested it on a 9-foot span, it was, because the stiffness of the specimen is relatively low when you have a 2-inch thick grout, and 9 foot was pretty long. So we pushed it as much as we could And, as you see here, we went to almost like 4.5 inch of deflection. This is for the span of L1 being 9 feet. So we went to 4.5 inch displacement, but the beam had not failed yet. So we kind of stopped the test. This was only really useful to get the stiffness information about the stiffness of the specimen. But then we did two more tests with this. One was 4 foot, and the other one was a L1 4 foot and L1 equal to 6 foot. Those are the two different spans that we. And the reason, by the way, we are testing this 2 inch because, as I'll mention in a minute, is that one of the potential applications of these SPiRe Plus panels could be in construction of roofs. So in roofs, typically right now you have your rafters or trusses every 1.5 or 2 feet apart. And that's primarily these, the controlled by the relatively small strength of the plywood that we use as the sheathing material for the roofs. So in this case, one of the benefits of using SPiRe Plus for a roof is that you can put your trusses or rafters farther apart. So you cut down on the number of trusses or rafters that we use. So here, for example, we tested it on what if you put your rafters 4 feet apart, or what if you put your rafters 6 foot apart? So these load deflections that you see here represent that. So with the 4 foot, we only went, so far and just stopped it because, again, we wanted to make sure that we get the stiffness of it. So that was good enough. We achieved, some good information there. But to get the strength of this, we used the 6 foot span. And on the 6 foot span, we went all the way to the end to make the beam to fail. And you notice that it failed at a load of about 5,700 or so pounds and a deflection of roughly 2.89 inches or so. That's that point, here in the top. So that was for the 2 inch thickness. So here are the summary of all three of these if you put them together. And, so we have beam B2, B3, B4. These are the dimensions. These are actually the moments from the test that we obtain. So these values, they represent in kip inches or kilonewton meters, but they are, remember, our test specimen was only 8 inch or 200 millimeter wide. So the way you would normally, you calculate your moments, for example, in the US customary, we do so many, kip feet or kip inches per foot width of your slab, or in the SI units, we do it per meter. So on the next column, I have put the normalized moment capacity of these. So kip inches per foot or kilonewton meters per meter width of the panel. And these numbers are then really for the 2-inch thick, 3-inch thick, 4-inch thick. These are the values that you can use for the design. And the applications, again, we have typically the first one, the thinner one would be for maybe a flat roof or slab. Then the 3-inch and 4-inch are typically repair of seawalls. And everything when you test in a lab, of course, everything fails. That's a given. But I wanted to focus on, don't lose sight of how good this product is, because here is the same load deflection curve that we had on the previous page. And then in this case, I have normalized the load. Instead of putting it in terms of pounds, I normalize it as pounds per square foot, which is what in US we typically use for design of walls or slabs. So if you notice, even though this thing, this is the 200 pound, this is like 200 pounds per square foot, 400 pounds. The values are so high. So I took this lower portion of the graph here and just blew it up here and put it on this upper corner. So this is 200 pounds per square foot. Typically a roof, for example, you would design it for 20 pounds per square foot. So that would be 1/10 of this. And if you see here, like this deflection is 1 inch. So if you look at here, if you're putting only 20 pounds per square foot on a span of 4 feet, you get a deflection of maybe about 0.05 inches, just tiny amount. And maybe if you're looking at the second graph, which was for a span of 6 foot. So let's say if you were going to put this on a 6 foot span, then you're getting a deflection of perhaps about 0.1 inch or so. So this is just really it is, these panels are pretty strong and stiff. So, and these numbers are obviously all within the allowable limits in most of the cases that we design. So I mentioned one of the problems with, one of the applications of this could be in construction of flat roofs. In recent wildfires that we've had in California, for example, these embers fly from the fire and they land on the roofs or in the attics and they cause fire on the roof. So a lot of times, a lot of these buildings, the fire starts from the roof and then it, engulfs the building below. So in this case, we can use, like right now we are testing this is what we had. We were using this panel SPiRe Plus that we have, but because it is 1.5 inch thick, we pour 2 inch of concrete or grout on it to make sure that at least it is covered all the way. So you could use in the field, if you were going to use this for example, for a roof, you would put a 2 inch or so or lightweight concrete or grout. The joints can be staggered. So here, for example, right here, this is one panel comes from here to here, ends here, and then another one comes from here to here. So there is a joint. So the adjacent panels, you can stagger the joints like a tile, so you don't have a weak point at one particular point. But keep in mind that if you use this as a roof, then even if the concrete had even if it did have any cracks, the water or any seepage of water would be caught by this bottom layer of FRP, which is like a continuous flat tray, if you will. So there's no water ever coming or leaking through your ceiling. So all of that maintenance issues with mopping of asphalt or other materials and maintenance and repeating the coating every few years, all of those things are really go away with this new type of roofing system. And as I mentioned, you can increase the spacing between the rafters or trusses, so that could save a lot of money in the overall construction of the roof. The other thing is that this panel, as you saw from the test, is really extremely strong. So if we were going to get into this market, and maybe if somebody, some of the engineers, we see if they're interested in using this, then we would be looking at making a weaker version of this for roofs, maybe just like 1 inch thick and fewer T profiles. And so you could put like only 1.5 inch of lightweight concrete on top. We also did a testing of these panels, as you see here, without any grout. This is primarily if you're, for example, if you're repairing a seawall, and let's say you're supporting bolts along the height of the wall, every 4 feet you have a bolt, anchor bolt. And then as you're placing the grout, at that point, you don't have a composite action between the SPiRe Plus and the grout because, the grout is wet. So the load is going to be taken by the SPiRe Plus panel only. And we did a test of this to see what kind of strength we get. Most applications would be, as I show in this graph, where you would be bending it with the flat portion being in tension, but we tested it both ways, this way and then flipped it over. And so if we go to the next video that I have here, this one is, so this is a test of that. You see how we are testing that with the flat piece of it on the bottom, and there's no grout in here, just 8 inches wide, and we're over a 4-foot span. We're testing it in a different testing machine at the lab. But here it goes, and you see, just watching it goes, it deflects quite a bit, it's flexible, but it is under a lot, and then it fades at a load of about 5,000 pounds. So these two graphs that you see are for both. In this case, one of them is the T profiles in tension or the T profiles in compression. So you have over a 48-inch span. This is what we get for the load deflection of these. And again, if you're designing a retrofit of an existing seawall and you're connecting these, over a 4-foot spacing along the height of the wall, you can see that, once again, the values go really high, but you never put 5,000 pounds of load on it. So typically you may be down in this corner, very tiny, very tiny displacements of less than point, way less than point 0.1 or 0.05 inch in terms of displacement. So that's something to keep in mind if you're designing those. And as we're getting to the end of our talk today here, I'm going to be at a couple of meetings that you might be, if you're interested in attending. One is I will be in Tampa next month, August 9th through 13th at the ASCE Pipeline Conference in Tampa. And then in September, I will be speaking at an international event in Panama. This is a SLUM conference, which is for all of the oil and offshore platforms in the oil and energy industry. It's a big conference. A lot of Latin and South American countries participate in that. So that would be I'll be giving a talk on September 26th, Friday, during that conference. And just one thing about one of our upcoming projects. It's a really interesting project. We have finished this is using SPiRe Plus. This is at the port of Long Beach. There are 4 of these dolphins. So as you see here, for example, this pile cap would be so difficult to repair conventionally. So we are repairing the pile cap with our SPiRe Plus, and then the steel pipe piles that are corroded in those structures, they will be repaired with our Pile Medic Plus, our shear wrap for load transfer and all that. So this becomes really a nice project where all of our marine repair products will be used on that project. The next thing is, just to remind you that here are a couple of links. If you'd like to scan this on the left, you can subscribe to our newsletter that we publish now. We've started putting it on LinkedIn, so I encourage you to do that. And thanks to Isabel, she's helping us. She's putting the links up there on the chat too. If you would like to copy them from the chat, they're the links for the same too. And then the one on the right is, remember I did these virtual lunch and learns to engineering firms. We also offer 1 unit of PDH. So if you're interested in learning a little bit more detail about our products and solutions, copy that, and that will take you to my calendar that you can select a scheduled date for your own office's lunch challenge. So with that, I think we've almost done close to the end of our 30 minutes. I'll end it here. If you have any questions, you could put it in the chat room, but if not, I appreciate you attending and watching it now or later, and I look forward to, if you have any projects or applications of these things, please feel free to reach out and we'd be happy to team up with you. I see no questions in the chat room. So have a wonderful day, everyone, and we'll see you hopefully in about a month or so.